This episode is supported by 23andMe. It's been said that the Apollo missions achieved all of the science goals that require live astronauts, that we no longer need manned missions to do science on the moon. Whether or not that's true, what about the science we can do from the moon? I'm talking about building a telescope there. Actually, China already has one. In December 2013, a Long March 3B rocket blasted off in southwestern Sichuan, carrying with it the Chang'e 3 lander. After 5 days of travel and another week of lunar orbit, it descended onto the surface and became the first soft landing on the moon since the Soviet Lunar 24 in 1976. It's been doing science ever since. That includes soil analysis, extreme ultraviolet observations of Earth's magnetosphere, exploration with an ill-fated rover, I'll come back to that, and of course, a telescope. The lunar-based ultraviolet telescope, LUT, isn't large at only around 15 centimeters diameter, yet it has one of the clearest views in the universe. See, the moon has essentially no atmosphere. That means, 1, the potential for extreme image sharpness with no turbulence to blur light from above. 2, Earth's atmosphere blocks all but a few narrow windows of the electromagnetic spectrum. From the moon, the entire spectrum is accessible. And 3, on Earth, sunlight is scattered to make our blue sky. On the moon, the stars are visible day and night. In addition, nights are especially great because they last a month due to the moon being tidally locked with the Earth. The LUT takes advantage of all of these, but its biggest advantage is that it can see into near ultraviolet wavelengths, out of the visible range observable within our atmosphere. Here's a UV picture of the Pinwheel Galaxy taken by LUT. Okay, so it's not quite the Hubble Space Telescope. But remember, LUT is only a 15 centimeter diameter scope. Some of you probably have bigger telescopes at home. I know I do. And the diameter of a telescope's aperture is everything. Not only does it allow the scope to collect more light, increasing sensitivity, but when you're in space or on the moon, aperture size defines image sharpness. We talked about this in our recent episode, Telescopes of Tomorrow. The diffraction limit defines the smallest resolution a telescope can achieve, and is inversely proportional to diameter. The LUT is a small scope, so its diffraction limit isn't great. But we can think of it as a proof of concept for building a much larger telescope on the moon. Normally, there's a pretty strict limit on how big a mirror you can get into space. It has to fit in a rocket. Even clever solutions like the upcoming James Webb Space Telescope's folding mirrors still have a limit. In addition, mirrors are notoriously fragile things. Subject them to the few G's of acceleration during a rocket launch, and you risk 7 billion years of bad luck. But on a platform as stable as the moon, it may be possible to construct a telescope mirror right there. In that case, there is no fundamental limit to its size. And there are plans. Big plans. I'm going to come back to a couple of the most promising in a moment, but before I do, let's talk a bit about why we've never sent anything larger than the cute little LUT. Two of the big challenges hit the Chang'e program pretty hard. So, Chang'e was named after the Chinese goddess of the moon. Her mythological pet is Yutu, the jade rabbit. Appropriately, Yutu is also the name of the rover sent with the Chang'e lander. Poor little Yutu was ravaged by the moon's harsh environment. It was gruesome. Let me tell you all about it. An extremely thin atmosphere confers several advantages, but it also has its issues. To start with, Earth's thick atmosphere is a powerful buffer against rapid changes in temperature. It warms up gradually during the day and cools gradually during the night. There is no such protection on the moon. When exposed to the sun, temperatures rise to around 125 Celsius, well above the boiling point of water. But put up some shade and temperatures drop to minus 150 Celsius or lower. During its relatively short roll on the lunar surface, Yutu was experiencing a massive temperature differential between its sunny side and shaded side. That fried and frozen rabbit stopped moving pretty quickly. Even with no mobility, Yutu's science instruments remained operational for a couple of years before succumbing to a worse problem. tiny shards of electrically charged glass. In other words, moon dust. See, without an atmosphere, there is no erosion of the lunar regolith. This is the upper surface of the moon that has been pulverized by 4.5 billion years of meteor impacts. When hit by sunlight, tiny regolith particles build up electric charge and so repel each other into dust fountains in the low lunar gravity. They stick to electronics, impede solar panel function, and grind away at moving parts. Nasty stuff. It eventually killed U2. Fortunately, the Chang'e's telescope is better shielded, and so it's still operational. However, the greatest obstacle to putting a telescope on the moon is, of course, getting it there. But in that challenge, this evil moon dust may actually be our friend. Perhaps we can build mirrors out of the stuff. Pete Chen at NASA's Goddard Space Flight Center proposes shipping a relatively small amount of epoxy and carbon nanotubes and combining it with a whole lot of moon dust to make a sort of concrete. Grind it into shape and coat it with aluminium, and it may be possible to build a 50-meter mirror on the moon. They've already built a 1-foot prototype and are planning a much larger test telescope here on Earth. Just as ingenious is the idea of a liquid mirror telescope. When a cylindrical container of liquid is rotated in a gravitational field, the liquid assumes a smooth parabolic shape, exactly the shape needed to bring light to a perfect focus. Liquid mirror telescopes already exist on Earth. The biggest is British Columbia's Large Zenith Telescope. It spins a 6-meter dish of mercury at 8.5 revolutions per minute, creating the cheapest telescope of that size ever constructed. The caveat is that it only points straight up. Tip it and the parabola is ruined, tip it too far and you spill mercury all over your grad student. But what you can't do with hardware, you fix with fast cameras and software to reconstruct a still image. It's also possible to correct with a movable secondary mirror. Pointing options are still limited, but by taking advantage of Earth or the moon's rotation, it's possible to scan a narrow arc across the sky. But mercury is expensive, heavy, and likely to evaporate in the moon's low-pressure atmosphere. Pete Warden, director of NASA's Ames Research Centre, and Ermanno Bora of the University of Quebec are working on a plan to instead use non-evaporating ionic liquids, basically molten salts, for the mirror base. They'll coat it with 50 to 100 nanometers of silver, which will solidify on the slowly flowing surface. Lower gravity could facilitate the formation of larger liquid mirrors, maybe up to 100 meters across. Such a telescope could gaze on the universe from when it was just 500 million years old. It's a cosmologist's dream, especially because cosmology tends not to require complex pointing. The whole liquid mirror configuration would weigh a few tons and could possibly launch in an Ares 5 mission in the 2020s. Maybe I'm biased by the cool factor, but this all sounds like a great reason to get back to the moon, robotically and in person. Plans are underway. More Chang'e missions will launch over the next couple of years. The International Lunar Observatory Association, in combination with Moon Express, form the first private enterprise to receive approval for lunar landing. They're hoping to set up an optical telescope, just 7 centimeters in diameter, which is small, but momentum is building. And Moon Express has a manned base in the planning, useful if we really want a giant lunar telescope. The moon, with its thin atmosphere, stable surface and long nights, is an astronomer's dream. If we can meet its distant challenges with creative solutions, perhaps the moon will become the Earth's lookout tower, granting the clearest views of all the rest of space-time. Thanks to 23andMe for sponsoring this episode. The name 23andMe comes from the fact that human DNA is organized into 23 pairs of chromosomes. 23andMe is a personal genetic analysis company created to help people understand their DNA. You'll be able to see which regions around the world your ancestors come from, understand how DNA impacts your health, and learn how your DNA influences your facial features, hair, sense of taste and smell, even sleep quality. Learning this information starts with just spitting in a tube, and within a few short weeks you'll see your results. I'm sending them some of my DNA, and I'll share the results with you on a future episode. My own background is Irish, And there's this one story in which one of my ancestors married a mermaid. I'm not sure whether they've fully sequenced the mermaid genome yet, but I'm really excited to see if there's anything really weird in my DNA. Go to 23andme.com/spacetime to support the show and learn more about your personal DNA story. As always, a huge thank you to all our Patreon supporters, and an especially big thank you to Shane Robinson, who just joined us at the Big Bang level. Shane, thank you so much. This is going to be an enormous help. Last week on Spacetime, we talked about time-space, the way time and space switch roles beneath the event horizon of a black hole. You guys had a lot of good comments. Feynstein 100 asks whether energy could be extracted from the flowing space-time inside a black hole. Well, not really from the flow of space-time actually inside the black hole. You could transform the gravitational potential energy of things falling towards the event horizon into usable energy. Quasars do this all the time to power their insane luminosities. Hydroelectric power plants on Earth do it with the flow of space-time that we experience as Earth's gravitational field. Falling converts gravitational potential energy into kinetic energy, but that kinetic energy is only positive relative to something that's not also in freefall. It's tricky to find a solid surface inside a black hole. One possibility could be in a Reisner-Nordstrom black hole, so one with electric charge but no spin. Here's a weird black hole fact. The electric field in a charged black hole at the singularity is expected to produce an anti-gravitational effect through negative pressure in a way that's mathematically similar to dark energy. So there should be a point inside such a black hole where this anti-gravity perfectly balances regular gravity and it's possible to float. You'd also expect that surface to contain a vast amount of energetic particles converted from infalling material. So I mean, you could try to use that energy for something, like being instantly fried. I see a whole episode here, so I'll leave it at that. NuclearCraft Mod spotted a missing plus sign in our full Schwarzschild line element. Wow, I bet you were a real pain for your professors. But you also give nice compliments, so I'm sure they forgave you for calling out their wrongness all the time. By the way, speaking of those extra angular components in the line element, AntiTwister over at the Spacetime subreddit had some interesting thoughts. He points out correctly that it's only the radial component that becomes time-like. The sideways components, angular or orbital components in spherical coordinates, stay space-like. But they become degenerate close to the singularity. That means that just before you reach the singularity, perhaps your sideways extent should wrap around and merge with itself just before you merge with the singularity. Sort of like a piece of tortellini, except that you'd be spaghettified before that happened. So do you get infinitely spaghettified before you're tortellini-fied? Sounds like a challenge question. Nezar Chahdi left this wonderful comment for anyone reading deep in the comment section. Hey Nezar, thanks for your kind words. My day is going great. I hope yours is too.